Hello, welcome back to part 2 on the law of sines. We're going to continue with our discussion on law of sines and pick up with the ambiguous case that was mentioned in the previous podcast on law of sines. In the previous podcast, law of sines, we looked at a couple different triangles. We looked at one where we know a side, an angle, and an angle. We looked at one where we knew an angle, side, and angle. The one with the ambiguous case we're going to look at is SSA, where you know two sides and you know an angle that's attached to that second side. And you're trying to find two other angles and a third side. In the previous cases, we knew two angles and one side. Now we know two sides and one angle. But this one can be a little bit tricky because even though you know what the side lengths are, once you make this angle here, you don't know what this third side length is. And as you're solving, you have to be careful because you could end up with a situation where the first side isn't long enough to connect with that third side. Or you might end up with a situation where it looks something like this, like side, no the angle, and it ends up being a right triangle. Or you could end up with one where it could end up with two triangles, like end up being like this, where your other side can either go here or go here, and then there's two possible triangles. So we have, and then also there's the possibility of just one triangle where it ends up connecting like that. So we've got to be very careful as we work through them. So I'm going to go through an example of each type of zero triangles. We're just not going to be able to do anything. Two triangles and one triangle. And then be able to compare and see what's happening there. Okay. Alright, first one, no such triangle. Let's say you have triangle ABC where you know angle C, and you know two sides, of course. And I'm not going to sketch this to be to scale or anything, but let's say you know angle C, and you know that it's 75 degrees 30 minutes. Okay, and then let's say you know side A. Let me label this first. Let's do A and B for the angles. And let's say you know side A is 17.9 centimeters. And let's say you know side B is kind of out there, but you don't know what the length is. And then you know for a fact that side C is 13.2 centimeters. Okay. I went ahead and sketched this as a complete triangle, but I don't know for sure whether I'm going to have zero triangles, one triangle, or two triangles until I start to work this out. And you'll see why as I start to work it out, and then I'll re-sketch it if needed. Okay, so I am set up here to do law of sines because I know angle C and side C, and I know side A. So I can say, alright, well, sine of angle C over side C equals sine of angle A over side A. So far, so good. Sine of 75 degrees 30 minutes over 13.2 centimeters equals sine of A over 17.9 centimeters. Alright, so we can go through, you can do some cross multiplying with the sine of 75 degrees 30 minutes and the 17.9 centimeters, and then divide by the 13.2 centimeters. And that'll tell us what sine A equals. Okay, so put that in the calculator here. sine of 75 degrees 30 minutes What did I do that for? Dang it. Accidentally tapped the clear button. Sorry about that. Let's try that again. Sine of 75 degrees. This thing's really sensitive sometimes. In 30 minutes. And then I was multiplying by 17.9 centimeters. And then dividing by 13.2 centimeters. And I get this. Alright, sine of A is about 1.313. So if I want to figure out what A is, I'd have to do the inverse sine of about 1.313. But I've got a problem here. Sine cannot equal something bigger than 1 or less than -1. The sine, the highest sine of theta is going to, the biggest it'll be is 1, smallest it'll be is -1. So this is out of the range of sine A. There is no such angle. Now, if you go ahead and try to do this in your calculator, you might say, okay, inverse sine of the second of answer, and then it gives you error domain, an error domain message. In other words, if you're trying to do the inverse sine of 1.313, that's out of the domain of the inverse sine. So it's not going to work. So I'll just go ahead and quit, and then it'll take me back here. So if there is no A that's going to work here, there is no triangle in this case. So what's happening is that you might have this 75 degree 30 minute angle here, and you might have 17.9 centimeters here, and you might have 13.2 centimeters there, but somehow this side isn't able to connect with that side. Like, you have to have this angle here, and then I'm not sure how long this side could be, but this one's not going to connect with it. There's just the way it's set up, it's not going to connect. So no triangle is going to work there. You know, it's possible. Sometimes problems are set up so that there is no solution to them. Alright, let's look at a situation where there's two possible triangles. Okay, next one. We have triangle ABC. I'm just sketching a triangle. I'm not trying to be accurate with the dimensions or anything. Okay, and what we know about this triangle is that angle A is 61.4 degrees. We know that side A is 35.5 centimeters. And we know that side B is 39.2 centimeters. Okay, we're going to start trying to use the law of sines to find our missing information. So we can start out with sine of 61.4 degrees, sine of A, over 35.5 centimeters, side A, equals, let's do sine of B over side B, 39.2 centimeters. Okay, so we'll go ahead and put this into our calculator here. We had sine of 61.4 times the 39.2. And then divided by 35.5. Okay, and then we're going to do the inverse sine of that. And we get around 75.81. Okay, so I did sine of 61.4 degrees times 39.2 centimeters divided by 35.5 centimeters. That answer equaled sine B, so then I did the inverse sine to get angle B. Alright, so angle B, 75.81 degrees. But wait a second. Let's think about this for a second. Think about our quadrants. Sine is positive here and positive here. When we did the inverse sine in our calculator, it went ahead and gave us the angle that would be in quadrant 1 that would make this true. But it turns out there's an angle in quadrant 2 that would also make this true. The reference angle for that angle is 75.81 degrees, but if you subtract from 180, you'll get the other full angle that has that same sign. (104.19 degrees). And that's totally possible with this triangle. So what could be happening here is you could have an acute triangle, or you could have an obtuse triangle that makes this work. So you've got to solve both scenarios. Okay, let's solve triangle 1. Triangle 1, we're going to use B being 75.81 degrees. Okay, if B is around 75.81 degrees and A is 61.4, let's use our calculators and figure out what the third angle would be. (42.79). That finishes finding the angles, because you already know that A is 61.4. Okay, you already know what side B is 39.2 centimeters. You already know side A is 35.5 centimeters. So then you could set this up and you could say sine of 61.4 degrees over 35.5 centimeters equals, and then you're trying to find side C. You don't know it yet. So you could say that equals the sine of 42.79 degrees over whatever side C is. And then use your calculators to solve that. So you got sine of 42.79 times 35.5. And then you're going to divide by sine of 61.4. And you get that. You get around 27.5 centimeters. So that's one possible scenario. Okay, and then triangle 2. A is 61.4 degrees. And then we found that B could be 104.19 degrees. So in that case, C, subtract those two from 180. Oh, 0.19. You get 14.41. So in that case, you know A and you know B. A is 35.5, B is 39.2. And then find C for this case. So you can do sine of 61.4 degrees over 35.5 centimeters equals sine of 14.41 degrees over whatever C comes out to. Okay. So we can do sine of 14.41 times 35.5 and then we'll take that and divide by sine of 61.4. And we get around 10.1 centimeters. So that one has two possible triangles, depending on what that angle B turns out to be. There's two possible answers for that inverse, for that sine there, that theta that they're taking the sine of. If there weren't two possible answers, then you'd only have one triangle. Let's say you have a triangle. Let's see, ABC. Again, I'm not drawing this to scale, but B is 68.7 degrees. C, A and C we don't know. Little b we know to be 25.4 inches. Little a we know to be 19.6 inches. Okay, so this one we could set up sine of B, sine of 68.7 degrees, over side B, 25.4 inches, equals sine of angle A over side A, 19.6 inches. Okay, use our calculators. Sine of 68.7 times 19.6, like that, and then divide by 25.4, like that. Now that's what sine A equals. And if you go and do the inverse sine, then you get the angle. So might as well round it to 46 degrees. The other possible angle isn't going to work here. If you've got 46 degree angle in quadrant 1, and you go ahead and draw the 46 degree reference angle in quadrant 2, the reference angle goes with a 134 degree angle. But but 134 degrees is too much. If you take angle B, 68.7, and add it to 134, you've already gone way past your 180 degrees that the three angles add up to. So in this case, the second angle is too big to work and make another triangle. So this is only going to make one triangle. So now we know angle A. We can leave that there. We can find angle C by adding these two together and subtracting from 180, and then finish solving. So 68.7 plus 46. Subtract from 180, you get 65.3. So that's the only possibility for angle C. And then we can say sine of 68.7 degrees over 25.4 inches equals sine of 65.3 degrees over whatever side C is. Okay, so sine of 68 or 65.3 times 25.4 divided by sine of 68.7, and you get 24.8. So side C is 24.8 inches. And now you've solved that oblique triangle. Okay, so there's your scenarios. You could end up with no triangles, two triangles, or one triangle. No triangle, you would get stuck right here. Wouldn't be able to do that inverse sine because the sine of the angle would equal something outside of the range of sine. Then you got two possible triangles in the case where you solve for your angle, but then there's another angle that would give you that same sine. When you do the inverse sine, you get the acute angle, but then if you subtract from 180, you get another angle that would work in that triangle. So you have to solve for two triangle cases. Or your third case is just one triangle, where when you do that inverse sine, you get an angle, and then if you tried to look at a possible second angle, it would be too big. It would make it to where you wouldn't, probably add up to more than 180 degrees, which doesn't work so well in a triangle. Alright, and then one more little topic to conclude this section. We'll talk a little bit about area of a triangle and how you can find it if you don't necessarily know things to plug directly into the A equals 1/2 BH formula. Okay, normally if you have a triangle, as long as you know the length of the base and as long as you know the length of the height, you can find the area. Area equals 1/2 times base times height. But you might not know all that stuff right away, and there is a way to use two side lengths and an angle to find area. Okay, let's take this triangle. Let's go ahead and label A here, B there, C there. We got capital A, capital B, capital C, and then call this capital D, this little point here. Our area of a triangle is 1/2 BH. The base here is B, we can leave that alone. But there's something interesting we can do with H. Turns out that the sine of angle A, okay, this A here is for area, whereas this A here is for the angle A. So two different A's. Alright, sine of angle A is going to be, for this right triangle right here, it's going to be opposite H over hypotenuse C. H height equals C times sine of A. Make a replacement in the area formula, and you get 1/2 B, and then replace the H with C sine A, and you get another way to find the area. It turns out there's other variations. Instead of using B and C, you can use A and B. And in that case, if you sign C, you're going to use all three letters. Like if you use B and C here, you'll have angle A. If you use A and B here, you'll have angle C. Or if you use A and C here, you'll have angle B. So you end up using all three letters in some way, in some fashion. Okay, so let's say you're given a triangle. It looks like this. It's triangle DEF. Alright, we got 9.0 feet here. We got 12 feet here. And we've got 127 degrees. And we want to figure out the area of this triangle. Triangle DEF. Well, here, we don't know the height of this triangle. The height would normally be from this very tip-top point straight down right there. But we don't know that, but you know what? We do know some other stuff. We know side F. We can find the area. We know side F, and we know, let's see, this is across from angle F, this is across from angle D. We know side D and side F, and we know angle E. So we can use side D, side F, and angle E. So we can take the 12 feet times the 9 feet times sine of 127 degrees. So we got 108 times the sine of 127 degrees. Let's see what that comes out to. Sine of 127, then times that by 108, and you get that. And you still have to do the 1/2 also. Sorry, squeeze the 1/2 in there. Haha. And then times that by 1/2. Woo! Divide by 2. Okay. So then you get around 43 square feet. And that's the area of the triangle. So if you know two sides and the included angle, you can use this formula, one of these formulas, to find area of a triangle. All right. Well, thank you for joining us for the rest of our Law of Sines adventure. It turns out that everything we were just doing a few minutes ago with those different cases, 0 triangles, 1 triangle, 2 triangles, turns out that we can also use something called law of cosines to solve that kind of oblique triangle, and we never have to worry about whether, like, figuring out whether there's 0, 1, or 2. With law of cosines, it all just works out and immediately tells you how many triangles there are. It's pretty cool. So you want to join us next for the video on law of cosines, and we'll talk about law of cosines, and I'll mention a little bit about where it comes from, and then we'll look at some examples of how to use it. And then we'll also look at another area formula that can be used if you know a triangle's semiperimeter and all 3 sides. It actually is derived from law of cosines. It's called Heron's formula, and we'll use it to find an area of a triangle too. So that's all in the next recording.